All right, guys, next lesson in our unit on circles is about secant, tangents, and angle measures. And basically what we're going to be doing here is we're going to be drawing lines through circles that intersect, sometimes on the inside, sometimes on the outside, and we're going to be able to relate those angles of intersection to the arcs that they intercept in the circle. And of course, before we get into this, we're going to have to define our new vocabulary, the most prominent of which is this term secant, which is probably a new word for you. So let's take a look at our new vocabulary. A secant is a line that intersects a circle at exactly 2 points. So if we've got our circle here, this guy, let's call him AB. This guy is a secant, okay? He intersects at exactly 2 points. That's as opposed to what we studied in the last lesson, our tangent, which is a line that intersects at exactly 1 point. We're going to bring tangents back for this lesson here, but I'll draw one just so we remember what a tangent looks like. So this guy's our tangent here. Let's say this is point T for the point of tangency, right? And this guy here is our secant. Now I know what you're thinking. Hold on, this looks kind of like a chord, right? Well, how is a secant different than a chord? Well, you could say that a secant is to a chord as a line is to a line segment. Notice the secant goes on infinitely in both directions, whereas our chord, we would say just that little piece there, that's the chord, right? But if you extend it in both directions like we do a line, you would say that's a secant. So you might say that a chord is to a secant as a line segment is to a line. That'd be a good analogy. Okay. Now, another thing that you're probably thinking is that you may have seen, if you recall your trigonometry in the last lesson, we talked about how this tangent is related to our trig function tangent, like the tangent of some angle theta equals the opposite side over the adjacent side. And when we looked at the unit circle, we saw that these are actually related. These are not two different things. Same word meaning two different things. They're actually pretty much the same thing. And so this term secant, if you've studied trigonometry in greater depth, you'll remember that the sine of some angle theta equals 1 over the cosecant of that angle theta. And we also learn that the cosine of some angle theta equals 1 over the secant of theta. Now, if you haven't seen this before, that's okay. This is some more advanced trigonometry, but you are going to run into this term. You're going to run into secant as a trig function, and it will be abbreviated like this. So is this using the same word to refer to two different things? Not quite. Let's take a look at the unit circle and see how it is related. All right, back to Mr. Rogers' augmented unit circle. When you get into Algebra 2 and Pre-Calc, you're going to see a unit circle that looks like this. You know, you're going to plot a point somewhere on a circle that has a radius of 1. And these points X and Y will help you figure out these different relationships on the unit circle. If you go beyond that into Mr. Rogers' augmented unit circle, you're going to find that if we extend these triangles outside of that unit circle, that this length right here is actually equal to the trigonometric function secant of theta. Okay, and as you can see, that is indeed, as it passes through the circle, that is indeed a secant. So the two terms are very, very closely related. They're not referring to two different things. You won't need to worry about this too much until you get into more advanced trigonometry in Algebra 2 and Pre-Calc, but I just wanted to show it to you so that when you see that term secant in both circles and trigonometry, you realize they're related. Okay, so let's take a look at our first theorem with respect to secants. Circle Theorem 12 tells us if two secants or chords intersect in the interior of a circle, then the measure of the angle formed is 1/2 the sum of the measures of the arcs intercepted by the angle and its vertical angle. All right, that's a mouthful. Let's see if we can look at this sketch here and just make sense of that. What it means is these two secants, RT and US, they cross inside the circle. They intersect here inside the circle, and we've created these two angles. Let's call them angles 1 and 2. It turns out that this angle 1 is going to equal 1/2 the sum of the two arcs that it intercepts with its vertical angle. Okay? So the measure of angle 1 here equals 1/2 the sum of arc RU, the measure of arc RU, plus the measure of arc ST. I like to think of it as if these secants intersect in the inside, the interior, then these angles formed are going to be the average of the arcs they intercept. After all, that is what we get when we add two things together and divide them by 2, right? We get the average of the two. So I like to think of this as the average. Okay, when they intersect inside, these angles formed will equal the average of the arcs they intercept. Let's try some examples. All right, here's our first example. Oh, and by the way, that theorem, circle theorem 12, don't forget, I am going to be creating a separate video where we prove this theorem, so you don't have to take it at face value. And you know what I say about that. It makes it easier to remember, and it's going to help you be able to rederive things that you've forgotten. So we'll prove this in the next video. Don't forget to watch that. In the meantime, let's see if we can just apply it. Here they want us to find x. You can see x is this angle formed here. You could also call this angle RVU. And notice this angle and its vertical angle intersect these two arcs. Okay, well, what we just learned in circle theorem 12 is that this angle inside x is going to equal the average of these two arcs, or we could say x is going to equal 1/2 times the sum of these two arcs, right? 52 plus 46. Good. All right, so we get x equals 1/2 times 52 plus 46 gives us 98. And 1/2 of 98 is 49 degrees. Good. So that's 49 degrees. Now, notice if you know this one's 49 degrees, you also now know this angle here as well, because they form a linear pair. And you also know this angle over here because they're vertical angles, and vertical angles are always congruent. And so we could say 180 minus 49 here gives us 131 degrees. So you can solve, once you know one of these, you can solve all of them. All right, here's a good chance if you want to pause the video and try this one on your own before I solve it. This one's just slightly different, but not too bad. I think based on the hints that I gave you in the last problem, you can figure this one out. They want us to find x, but interestingly enough, they don't tell us the measures of the arcs that it intercepts, right? They're not telling us this, so I can't go straight ahead and find x. What if I found this angle y, though? Could I find this angle y? I can find y because I do have the arcs that it intercepts. All right, so I know angle y is going to equal the average of those two arcs. It's going to equal 1/2 times the sum of those two arcs, 89 plus 47. Okay. All right, so I get y equals 89 and 47 gives me what, 136, is that right? So half of 136 is going to give me what, 68? Is that right? 68 degrees. You're not trusting me on that math, are you? Yeah, perhaps you shouldn't. Remember I said, never trust your math teacher. 136, yep. And we get 68 degrees. Okay, so y is 68 degrees. But that's not the question, right? They want us to find x. So these guys form a linear pair. They're going to be supplementary. So 180 minus 68 is going to leave me with 112 degrees. So x is 112 degrees. Good. All right, next theorem, circle theorem 13. And this says, we looked at two secants earlier. Now we're going to look at a secant and a tangent. And if a secant and a tangent intersect at the point of tangency, right here at point T, then the measure of each angle formed, this angle 1 and this angle 2, each of these angles, their measure is going to be 1/2 the measure of its intercepted arc. In other words, this angle 1 right here is going to equal half the measure of this arc TSR that it intercepts. And this angle 2 is going to equal half the measure of this arc RT that it intercepts. All right, I know how you're feeling right now. You're like, wow, there's lots of circle theorems. We're on 13 already. This is a lot of stuff to remember. So how do we remember this without really stressing ourselves out? And the way I like to think of this is, it's exactly like an inscribed angle. Pretend that I had some inscribed angle right here. Just pick an angle right there, okay? Well, you can see this angle intercepts this arc TSR, right? And we know that this angle, let's call it angle Z. We know that the measure of angle Z is going to equal 1/2 the measure of arc TSR, or RST. Let's go in alphabetical order, right? Okay, that's our inscribed angle theorem. We're comfortable with that. Okay, notice also that I can just grab, if this was like string and I had a pin, I could grab this vertex and I could move it anywhere on this arc, and it still intercepts the same arc. And therefore, even as I move this vertex, this angle does not change. In fact, I could move it all the way down to here until it just suddenly ceases to be an inscribed angle, and now it's just this angle here, right? So it's understandable that at that point, this inscribed angle would still have that same measure, that 1/2 the measure of this arc RST. Okay, that's how I like to visualize it and remember it. Now, there is a proof for this, and it's a very cool proof. So don't forget to tune in to the next video, and I will do all the proofs of all the theorems in this lesson. The proof will help as well, but sometimes a little visual is just really kind of gets right to the point. And if you picture this as an inscribed angle that just suddenly, all of a sudden, disappears, it's a little easier to remember that this condition, this angle 1, will equal half the measure of this arc it intercepts. Let's try some examples. Here, could we find the measure of angle EBD? So they're looking for this angle right here. Could we find that? Well, we know this is going to equal, since this is a secant and this is a tangent, this is going to equal 1/2 the measure of the arc it intercepts. The arc it intercepts is right here. If we come all the way around, this is arc ECB, and that has a measure of 230 degrees. So we can say the measure of angle EBD is going to equal 1/2 the measure of arc ECB. In other words, the measure of angle EBD is going to equal 1/2 times 230 degrees, which is going to be 115 degrees. Good. All right, let's try another one of those. This one's a little bit different. They want us to find the measure of angle EBA this time. Okay, now there's a couple different ways you could approach this. You could find this angle and then say, well, these two are supplementary, and just subtract from 180 to get this angle. You could also say that this circle, hold on, that whole circle is going to be 360 degrees. So I could subtract this 254 degree arc, and I would be left with this 106 degree arc over here. So maybe you want to try it that way. And then you can say that the measure of angle EBA is going to equal half of this arc that it intercepts. 1/2 times the measure of arc BE, right? 1/2 that measure, which is going to be 1/2 of 106, which is going to give us 53 degrees. Notice you could have also said, all right, I'm going to find this angle over here. This angle is going to be half the measure of the arc it intercepts. So this angle over here is going to be, what do we got? 120, half of 254 gives us 127, right? So that'd be 127 degrees, which is good because guess what? That's supplementary to this angle right here. Between the two of them, this angle in here is 53 degrees. 53 and 127 add up to 180. Good. All right, another one like that with just a little bit of a twist. Here, this time they want us to find the measure of arc EB. Let's go ahead and highlight that. They want us to find this arc right here. Okay, can we do that? Well, maybe the easiest way is to take this linear pair, and if this angle is 128 degrees, let's figure out what this angle is going to be. I think this angle in here is going to be 52 degrees, right? And those add up to 180. All right, so that means that this arc, that equals 52 degrees, equals 1/2 of the measure of arc EB, right? Or I could multiply that whole thing by 2 and get 104 degrees equals the measure of angle EB, right? Remember, the arc is going to equal twice the measure of the angle. The angle is going to be half the measure of the intercepted arc. Good. Okay, now we've got another circle theorem here. We're up to 14. And this is not as intimidating as it looks, so stay with me on it. It just happens to be that there's 3 conditions that happen when secants and or tangents intersect outside the circle. So we're going to take a look at those. Basically what this is saying is that if 2 secants or a secant and a tangent, or 2 tangents intersect in the exterior of a circle. Now we're outside, not inside. No, we're not inside, nor are we on the circle. We're outside. In this case, the measure of the angle formed is 1/2 the difference of the measures of the intercepted arcs. So remember, when we crossed inside, we were 1/2 the sum of the intercepted arcs. When we're outside, our angle is going to be 1/2 the difference of the intercepted arcs. So, for example, here's a case where 2 secants intersect outside the circle at point E. Point E is our vertex, so our measure of angle E is going to be 1/2 of the difference between these 2 arcs, JK and FG. This angle will equal 1/2 of the difference between JK and FG. JK minus FG divided by 2 gives me the measure of that angle E. We could also have this case here where a secant intersects a tangent outside the circle. Okay, same thing here. This angle is going to be 1/2 the difference between these 2 arcs. This time it is 1/2 the measure of arc JG minus, I should use a different color here, right? Minus the measure of this arc FG, right? I'll see if I can fix this one up there. A little sloppy, but. All right, so very similar, even though this time it's a secant and a tangent. It's the same idea. Because the vertex is outside the circle, it's going to be 1/2 the difference in those 2 arcs. Last one, what if 2 tangents intersect outside the circle like this? Well, it's the same thing. It's going to be, this angle E is going to equal 1/2 the measure of, or 1/2 the difference in the measure of arc FJG. So let's highlight this guy in green. 1/2 times arc FJG minus this arc FG. Okay? So this applies to secants and tangents anytime they intersect outside the circle. 1/2 the difference in the intercepted arcs. All right, let's try an example here. Here they want us to find the measure of this angle E. And this looks to me like we've got 2 secants intersecting outside the circle. Okay, so I'm going to say that the measure of angle E, that's going to be 1/2 times the difference in these arcs. Arc JK minus arc FG. Good. All right, let's go ahead and plug in what we know here. We know that arc JK is 116. Minus this arc FG is 42 degrees, right? So I'm going to get 1/2 times 116 minus 42. What does that give me? It gives me 114 minus 40, 74. So 1/2 of 74 is going to give me 37 degrees. Okay, so if this angle here intercepts these two arcs, measuring 42 degrees and 116 degrees, I know this is going to be 37 degrees. By the way, yes, I know what you're thinking. Are we going to prove these as well? Yes, in the upcoming video, the next video, we're going to prove all three of these as well. Some very cool proofs, so make sure you tune in for that. Let's do another example like this. Could we find the measure of arc FG? Okay, this time they give us the angle where the two secants intersect, and they give us one of the arcs. Could we find the other arc? Shall we call this, let's call it X. If we don't know what it is, we call it X, right? All right, so we know the exterior angle is going to equal 1/2 times the difference in the two arcs, 86 minus X, right? So I could go ahead and, now, if you want to distribute the half, you can. But I know you guys don't like to work with fractions. And, you know, you don't have to if you don't want to. If you multiply the entire thing by 2 rather than distributing the 1/2, that's a good trick to remember. Really, we're distributing the 2 all the way across the whole equation, right? 2 times 28 gives me 56. 2 times 1/2, of course, accomplishes what we were after, getting rid of the fraction. And all we're left with is 86 minus X. That cleans up really nice, doesn't it? All right, so let's go ahead and subtract 86 from both sides. I know some of you are nervous because you're seeing negative numbers, and we don't do negative numbers in geometry, right? 56 minus 86 gives me negative 30. But I'm left with negative X. So if negative 30 equals negative X, what does positive X equal? 30 degrees equals X. So the measure of this arc here is 30 degrees. If we intercept at 86 degrees out here, and this angle formed is 28 degrees, then this arc here must be 30 degrees. All right, here, slightly different problem, but same idea. They want us to find the measure of arc FJG. So this guy here all the way around. They want us to find this guy. And this time we don't have two secants, do we? What do we have? We've got two tangents intersecting outside the circle. But the key here is that the intersection point is on the exterior of the circle, and we're dealing with tangents and or secants. So we can say that this angle formed must equal half of the measures of the arcs it intercepts. So it must equal half of, shall we call this arc that we're looking for, shall we call it X? 60 degrees must equal half of X minus 120. Okay? All right, if you want to blast out that fraction by multiplying the whole equation by 2, you can do that. We get 2 times 60 is 120. 2 times 1/2 makes it go away, and we get 120 equals X minus 120. Solving that for X, we're going to add 120 to both sides. And we get 240 degrees equals X. Now I know what you're thinking. Hold on, Mr. Rogers, that's silly. Why'd you go through all that? I could see that this was a whole circle. In these two arcs or adjacent arcs, a minor and a major arc, and together they're going to have to add up to 360. I was going to skip all that and go right to X equals 240 degrees. You can, but in a sense we kind of just proved our theorem of intersecting tangents, didn't we? Okay, what is Dave up to now? Dave is shining his flashlight on a glass rod. So picture like a dowel that's made out of glass, and this would be the cross section of it, right? So he shines his flashlight on a glass rod, which causes the light rays to refract at points G, J, and K. So like a light ray comes in and comes out, and it's refracted, it's bent. If the measure of angle E is 15 degrees, okay, I'm going to go ahead and label that. They're telling us the exterior angle formed here is 15 degrees. And the measure of arc JK, so this guy over here, I'll just label him as 50 degrees, right? They tell us that. Could we find the measure of arc FGH? So this arc highlighted in pink here. Okay, well, that looks like my case of two secants intersecting outside the circle. So I could say that this external angle 15 degrees is going to equal half the difference in the two intercepted arcs. We don't know what this one is. We'll call it x, right? So 15 degrees will equal half of 50 minus x. All right. If you want, get rid of that fraction, multiply the whole equation by 2. 2 times 15 gives me 30 equals 50 minus x. Subtract 50 from both sides, and we get negative 20 equals x. Oh, excuse me, equals negative x, right? And therefore, x equals 20 degrees. Okay, so if these secants intersect at an angle of 15 degrees and we're intercepting an arc of 50 on this side, then we're intercepting an arc of 20 degrees on that side. Okay, all right, quick summary of all the things, because there's a lot of theorems we've learned in this lesson. Oh my goodness, what is this? Look at that. There we go. Okay, quick summary of our secant-tangent angle theorems. And this is a good way to remember these. If we have the vertex, this is probably the best way to summarize these things so that we can recall them when we need them. If the vertex is on the circle, think of it as an inscribed angle. Even if it's this case, where it's a secant intersecting a tangent, still think of it like an inscribed angle. Okay, we know that if the vertex is on the circle, that the angle will equal 1/2 of the measure of the arc it intercepts. In this case, we've got these arcs labeled as all being x degrees. So in this case, angle 1 is going to be half of x degrees. Another case, what if the vertex is inside the circle? Boom, boom, we've got these two secants here. In this case, angle 1 is going to be half. Oops. It didn't print. Sorry about that. It's going to be half of the sum of these two angles, x plus y, right? So, or you can think of it as the average, right? Take the average of those two arcs. Same thing here. My 1/2 didn't print. It's funny. What if you have this case where the vertex is outside the circle? Okay, in this case, whether they're two secants, secant and a tangent, or two tangents intersecting outside the circle, this angle formed, this angle 1, is going to be 1/2 the difference in the two, x minus y. You could think of this as 1/2 the sum. You can think of this as 1/2 the difference. Okay. All right, that's my lesson on secant, tangents, and their angle measures. I hope you guys found this helpful. The number one thing you can do to help you remember these theorems more is to just practice them. So make sure you tackle all the homework, do the homework problems, and don't forget there's an accompanying video that proves all these theorems. So you don't just have to take my word for it. Give you a little bit of extra practice on proofs, and hopefully help you remember the theorems a little better. All right, guys, thanks for watching.